So now let's talk about what these values actually mean for us. Why does it matter what our median, our mean, and our are? And what do these skewness and kurtosis statistics actually represent? Okay, so I'm going to pop over into PowerPoint. And we're going to first talk about the 5 features of a normal distribution. Again, I'm going to breeze through this. Hopefully, this is revision for you guys. If not, I recommend going back through some of the revision slides for 105. So, when we talk about a normal distribution, we're talking about what our frequency distribution looks like. Okay, so remember a frequency distribution is essentially a bar graph where each bar represents the number of participants or the number of individuals in each value. And if a data set is normally distributed, it will have all 5 features of a normal distribution. So the first one we've talked about a little bit already, and that's central tendency. Central tendency just means that in our data set, there's a tendency of values to cluster around our mean, median, and mode. And this is what's considered a bell curve. So if we fit a curve to our distribution, it almost looks like a bell. Now this here is a perfectly normal distribution. Generally, in the real world, you won't see a perfect distribution, a perfectly normal distribution, but we just want to make sure that our data essentially follows these assumptions, right? And you can see in this distribution, our mean, median, and mode are all at the same spot. And this looks to be at about a value of 75. The next assumption is simply that our distribution has variability to it. And this just means that our standard deviation or variance is greater than 0. It depends on the scale of your data, whether your standard deviation is going to be 1 or 50. That is not quite as relevant. It just depends on the scale that's going to define your standard deviation. So if we go ahead back to Stata, looking at our summarize command, let's take a look at IQ. So this middle table here. If we want to find the median value for the IQ score, again, we're going to look at this 50% row, and we can see that IQ of 100 is the median of our distribution. And the mean here is 100.26. So those are very, very close. Again, the summarize command isn't going to tell you the mode, but if our median is 100 and our mean is just at about the same place, we can assume that our mode is going to be around that value as well. Right? We can also see that this variable has some variability to it. 12.98 is our standard deviation. So that looks good. Right, and the next assumption of interest is going to be skew. And this refers to how symmetrical our data set is. So if we look at our previous distribution, we can see that it's pretty much symmetrical. It's mirrored on either side of the mode. So if there is a skew in our data set, this means that our tails are not going to be symmetrical. So we can see here what's considered a positive skew. This right tail kind of lingers out much further. And then conversely, a negative skew, we have the left tail. That's much longer compared to the right tail. I remember a positive skew because if you follow the tail, it's going in the positive direction. Whereas a negative skew, if you follow that tail, it's going in the negative direction. Okay, so we have a positive distribution here, a positively skewed distribution, and a negatively skewed distribution here. This is really important because a skew is going to not only have a skew to the data, but it also means that our mean, median, and mode are not going to be at exactly the same spot because this tail here is going to be pushing our median and our mean away from the mode, or again, the mode is the most represented value in our sample. So our mode is always going to be the peak here. So our mode is in blue. Now, whereas a normal distribution, the mean, median, and mode are on top of each other, our median is actually going to be shifted over to the right, just a little bit. But the most impacted value by this skew, or by these potential outliers, is our mean. So our mean is going to be pushed over much further to the right compared to our mode and our median. And that's because these data out here are going to be heavily influencing the average value of our distribution. Okay. Now, of course, you can tell if your data are skewed by just visualizing the frequency distribution, but Stata will also tell you a skewness statistic. Now, a perfectly normal distribution will have a skewness statistic of exactly 0. Again, in the real world, you will probably never have a skew statistic exactly 0. Um, so any value less than 0 will represent a negatively skewed distribution, and a value greater than 0 represents a positively skewed distribution. But now, again, anything close to 0 is probably okay. You really want to look at your skewness statistic in conjunction with your frequency distribution to confirm whether there's a skew to your data set. So if we head on over to Stata again, we can see in our detailed summary table, a skewness statistic for IQ is 0.39. So that would suggest a slightly positive skew to our data set. Okay, and we can confirm that with a frequency distribution again, which I'll show you in just a little bit. But again, a value fairly close to 0 should suggest an adequately normal distribution. This would probably suggest a slightly mild skew, which might not be problematic in the long run. Many of the analyses that we'll be learning in this unit are really robust to violations of these assumptions of a normal distribution. Later on in this unit, we'll talk about alternative analyses if we are violating assumptions, um, but you'll cover that much more heavily next year. Right, so let's talk about kurtosis next. And kurtosis sort of defines how flat or how pointy a distribution is. More importantly, kurtosis tells us how much data is represented in the tails on either side. So a perfectly normal distribution is considered mesokurtic. So this distribution here would be considered mesokurtic. Okay, and that means you have some variability and you have variability in the tails. Okay. This can be a little bit more difficult to visualize than a frequency distribution, so your test statistic is going to be really important. And in Stata, the kurtosis test statistic of 3 is considered mesokurtic. Okay. Platykurtic is represented by values less than 3 in Stata, and this means you have quite a bit more data in the tails here. So you can see that you have a lot more data in these tails compared to a mesokurtic distribution. And again, that's represented by kurtosis value less than 3. One way you can remember this is a platykurtic distribution almost looks like a flat plateau. Okay? And finally, a leptocritic distribution means that you do not have very much data represented in these tails, and usually the peak will be much pointier. That's considered leptocritic. And again, that is represented in stata by values greater than 3. Another way that I remember um, which values in stata represent leptocritic, mesocritic, and platycritic. We know that 3 is our standard for a normal distribution, and that's mesocritic. And you can see here the peak is right in the middle. For a leptocritic distribution, values greater than 3 are represented in stata, and our peak is much higher than a mesocritic distribution. For a platycritic distribution, we'll see values less than 3, and the peak here is much lower. So that's just how I remember which values in stata represent meso, platy, and leptocritic distributions. All right, so let's go ahead and take a look at our variables again. Right, if we're sticking with IQ, we can see we have a kurtosis statistic here of about 2.78. Just like with our skewness statistic, we'll probably never see or rarely see a kurtosis statistic that's exactly 3. So somewhere around 3 is going to be just fine. But because the kurtosis statistic is a little bit less than 3, that suggests a slightly platycritic distribution. It might not be problematic distribution, but it would be slightly platycritic. And again, that means we have a lot more data in the tails compared to a normal distribution. Okay. And the final feature of a normal distribution is modality. Now, this can really only be visualized. There's no test statistic for modality, but it's also fairly easy to visualize. Usually, a non unimodal or a multimodal distribution will look pretty extreme. And modality essentially tells us how many humps or how many modes there are in our data set. So a unimodal distribution will have one very clear mode, as the name suggests. However, a bimodal distribution would have two clear modes. You can also have 3 modes, which would be considered multimodal. This is really important because not only do we have two seemingly distinct distributions going on in this data set, but our mean is also going to not really be representative of the sample. So our mean would actually be around this dip here. And same with our potential median, whereas we have two distinct modes. Now again, there's no test statistic to determine if your data set is multimodal versus unimodal, so you do have to visualize using a frequency distribution. So let's go ahead and do that now in Stata. If we go back to our do file, let's first run the frequency distribution for IQ. And the command here is just histogram IQ. Now, there are ways to visualize each frequency distribution at the same time, but that includes a fair bit more syntax. So I'm just going to go ahead and demonstrate individually. So we can, if we run that command, we can see our frequency distribution for IQ. If we really quickly review the summary statistics, we confirmed that the median and the mean are pretty similar, so we do have central tendency. There is variability, which is good. It's a slightly positively skewed distribution and slightly platykurtic. And all of that can be confirmed from our frequency distribution here. We see there's definitely a positive skew, and there's also a fair bit of data in the tails suggesting a platykurtic distribution. Now let's do the same thing with our two other numeric variables. And let's look at ADD-like behavior score first. So we have a skewness statistic here of about zero point 0.4, which would suggest, again, a positive skew. A kurtosis here of 2.95, which is incredibly close to 3. So there we would conclude that this is mesokurtic. And it looks like overall we have central tendency. Again, just like with variability or standard deviation, with a range from 26 to 85, a median of 50 and a mean of 52.6 are pretty close together. Now, if we had a range, say only from 45 to 55, this difference of about 2.6 would be a little bit more concerning. But again, because we have such a large range of scores, this probably isn't, this would suggest central tendency. Okay, so let's confirm all of that with the frequency distribution. And the command there is just histogram ADD score. And as the summary table suggested, um, the data do look pretty mesokurtic. We have a nice bit of data in the tails, but not too much, not too little. And there does appear to be a slight positive skew. Now, the important thing to remember about our descriptive statistics and our frequency distributions is that we really want to get an accumulation of evidence to come to the conclusion whether our data are normally distributed or not, so that we can go forward with our analyses.